Good morning, AP peoples. Hey, so I know I did this in class with most of you, but there was a class where we got interrupted on this. So this is the conservation of energy roller coaster example. So I plan on building a roller coaster out in the quad by the PAC, and my plan is to have a 500 kilogram roller coaster car go up to a first hill, which is 10 meters tall. That's the top of the PAC. Come roaring down to the ground again. Again, the ground is H equals 0 level. Then go back up to a second hill, which is half as high, 5 meters high. And then we're going to bring the car to a stop by having it compress a spring whose spring constant is 5,000 newtons per meter. And so I'd like to do some calculations and see what's going on here vis-a-vis energy, and use the concepts of conservation of energy. So we know in this section here some work is going to be done by whatever chain that runs under the track and hoists the car up to the top. When it gets to the top, it's going to have potential energy. I want it to get to the top with no velocity, so maybe I'll draw a little car up here. I want it to be released from the chain with just negligible velocity. And then you immediately start rolling down. Now, when you get to the bottom of the first hill, you will be going as fast as you can go. When you get to the top of the second hill, you'll still be going, just not quite as fast. And then, of course, here we are about to crash into the spring and be brought to a stop. Back to our analysis of energy, we have potential energy at the top. We have kinetic energy here at the bottom. And here we have a mixture of potential and kinetic, otherwise known as mechanical energy. And of course, we'll have potential energy when we compress the spring. So maybe I should mention that these gravitational and this is spring, or I'll just mention that that's spring. Okay? And the whole point of the law of conservation of energy is that the amount of work done here will be exactly equal to the potential energy at the top of the first hill, will be exactly equal to the kinetic energy at the bottom of the first hill, will be exactly equal to the sum of two energies here, and exactly equal to the energy stored in the spring when we finally bring the car to a stop. So, we can try to figure out what that is. And if we set about trying to figure out, let's go ahead and mark these things up. This is going to be section A, section B, section C, section D, and section E over here. If we try to find the work for section A, we're kind of stuck because work is force times displacement, and we could figure out the force if we knew the angle, because this is an inclined plane, and we could figure out the displacement if we knew the angle, because we have this opposite side and we're looking for the hypotenuse of a triangle, but we don't really have either of those because we don't have the angle. So this is going to have to be a wait and see thing. So let's go ahead and find the potential energy at point B. That we can do because that's m times g times h, and we have all those numbers: 500, 10, and 10. And that is 50,000 joules. So our energy budget, ladies and gentlemen, is 50,000 joules. We now know that 50,000 joules of potential energy is had here at the top. That means that we can now write in that this must have been 50,000 joules. We'll have to have a motor or whatever that can impart 50,000 joules to this car. That also means that we understand that the kinetic energy at point C is going to be 50,000 joules. And that the sum of the potential and kinetic energies at point D is going to be 50,000 joules. And the potential energy in the spring will be 50,000 joules. And now you can ask all kinds of questions and answer them very quickly. One question I might want to ask is, hey, what is the velocity at point C? Okay, well, let's solve that problem. The velocity at point C, we can answer that question by saying that this potential energy at the beginning, which is 50,000, but I'm going to write it just as U because I want to do this with all symbols and show you some cool stuff, is going to turn into kinetic energy. So that's at point B, and this is at point C. Okay, that would mean that m times g times the height of hill B is going to equal 1/2 m times the velocity at C squared. And the m's cancel, which is cool. That's why I didn't want to put just 50,000 in here. We already know this is 50,000, but you would not have been able to see that the m's cancel. Multiply both sides by 2, you got 2GHB equals VC squared, or VC is going to be the square root of 2GHB. Put the numbers in for that, and you get to discover that VC is 14.1 meters per second. Not a very high velocity. It's about half of freeway speed, so 32 miles an hour. But again, this is only 10 meters tall. This is an Adventure City roller coaster, not a Six Flags Magic Mountain roller coaster. So another thing we could try to figure out is what is the velocity at point D? Well, for that one, we would say that our energy budget, that is the potential energy at point B that we calculated earlier, is now equal to the potential energy at point D plus the kinetic energy at point D. So m times g times the height at B is going to equal m times g times the height at D plus 1/2 mvd squared. Okay, the m's all cancel and we'll multiply through by 2. We get 2ghb equals 2ghd plus vd squared. Bring these together and take a square root. Okay, I'm going to bring this one to the other side. I'm going to factor out the 2g. Let's just do that much right now. And you can see that this is going to depend entirely on the difference in height between this hill and this hill. That's kind of cool. The only thing that matters in the speed is the difference in height. So had we had the track go down and back up, it would be the same as if we had the track go straight this way, or even horizontal and then drop down. It would have been the same. This is to a square root. Sorry. There we go. Now we're in good shape. And if you put the numbers in for this, you get 10 meters per second. And this is kind of cool. VD is 10 meters per second. I want to draw your attention to something. Hill 2 is half the height of Hill 1. So we went from the top all the way to the bottom and got 14 meters per second. We're halfway back up, but we don't have half of 14 velocity, or 7. We have 10. We have more velocity than you would expect, and that's because velocity is squared in the recipe for kinetic energy. Although the height is linear for potential energy, velocity is squared. So its behavior is a little different. You retain more velocity. It makes the second hill on a roller coaster kind of exciting. And the final thing we can do is figure out how much distance do we need here in order to stop. In other words, I need a spring that has this spring constant, but it needs to be long enough to stop the cart. So what we need to do is say that the potential energy at B, that's our original energy, D equals question mark, is going to equal our potential energy in the spring. And that means that m times g times hb equals 1/2 k x squared. Well, x here is going to be the distance that I'm looking for. So I'm going to substitute in a d there. Let's just put right here 1/2 k times d squared. All right, now we already know that m times g times h is 50,000. And the reason I'm not canceling the masses is there's no mass on this side, so it doesn't do the cool thing that it did up here when you involve a spring. So 50,000 equals half of k, or 2,500, times d squared. 50,000 divided by 50,000 divided by 2,500 is 20, and so d squared equals 20, and d is going to be about 4.5 meters. I'm going to need a pretty long spring and a long space to stop this thing, just to make sure I don't, run out of spring compression. So there you go. This is the example I did in class, just showing you how to set up the problem, showing you that all these energies are equal to each other, and you can use that to solve for various things. All right, thanks for your attention.